When you are tossing a coin, either you get a head or a tail. An item manufactured in a company, either good or bad. Fruits in a basket is either good or rotten. And when we are selecting them, either we get the success. When we are choosing, the item chosen may be good or may be bad. Okay? All these are called either success or failure. Getting good item means it is success. Getting a head when a coin is being tossed, that is a success. But people can say that no, getting a tail is also a success. That is different. But normally getting a head is a success. If we roll a die, getting a 6 is a success for us. Somebody has told that success is getting a 6. So getting a 6 is a success for us. Not getting a 6 is a failure for us. This kind of experiment, when you perform and whose outcomes are success or failure, then we say that a trial is made and the result, outcome of the trial or the experiment, trial of the experiment is either success or failure. These kind of situations when arise in probability, dealing many number of cases, not possible by ordinary definition of probability distribution. Number of trials going to be more, we cannot deal with just by definition of probability distribution. We need binomial distribution for it. Hello everyone, MK is here. This session we are going to discuss binomial theorem. But binomial theorem has one history over there. Like history means how binomial theorem arises, that I'll explain step by step, one by one. But first, I'll be defining what is the meaning of Bernoulli's trial. Actually, binomial distribution, the concept was given by Bernoulli, the famous mathematician, you must have heard. He gave the concept of binomial distribution. But before that, we need to know what is Bernoulli's trial. All those trials I told you are said to be Bernoulli's trial if following conditions are obeyed in the trial. And in this discussion, I hope all of you have understood that getting a success or failure are not dependent on each other. In one trial, suppose I have tossed a coin 50 times. Then number of trials is equal to 50. In a trial, we are getting success. Next trial, we are getting failure. Getting failure over there is not dependent on getting success in the first trial. Okay? All these will constitute Bernoulli's trial. So for a Bernoulli's trial, when you say that a trial, that experiment is Bernoulli's trial. Trial is said to be Bernoulli's trial if the following conditions are obeyed. What are the conditions for Bernoulli's trial? Let me list. That Bernoulli's trial outcomes are either success or failure. We have started that manner. Only two outcomes are there and events are independent. Okay? So let us write the first point here. Trials are independent. getting a success in one trial will not ensure you failure in the next trial. You can get next time also success only. Number 2, number of trials must be finite. Finite number of trials will be there. Infinite number of times you are continuing the experiment. That is not true. Okay? And there will be only 2 outcomes. Only 2 outcomes means either success or failure. Success will be taking as S. Failure, that outcome will be taking as F. And number 4, probability of success will remain the same in each trial. So similarly failure also. Probability of success or failure remains the same. Let me explain Bernoulli's trial again. First thing, trials are independent. Which one will be our next occurrence, that we don't know. Independent. I mean, for first, second or third trial, what you are getting. Fourth trial, what outcome you get, that is not dependent on the previous trials. Number of trials finite. You cannot perform the experiment for infinite number of times. You cannot try for infinite number of times. And only 2 outcomes are there, either success or failure. All 4 points are very important. And probability of success or failure remains the same. Suppose you are tossing a coin 80 times. So probability of getting for an unbiased coin, P will be equal to half. This will be constant, and Q also half, because P plus Q in one trial will be equal to 1. You know sum of the probabilities equal to 1. Clear? You understand what is Bernoulli's trial then? If one mark question arise based on this concept, you can answer easily. What is Bernoulli's trial? Okay. Let us take one example, that urn contained 10 red and 15 black balls. You are selecting, say, 5 balls one by one. 5 balls are being selected one by one. 5 balls are being selected one by one. Number 1 with replacement, and number 2 without replacement. Okay. Just tell me, during this experiment of choosing 5 balls, whether this we can refer as Bernoulli's trial or not. This will be Bernoulli's trial or not. First case, suppose I told you getting red ball is a success over there. Then for first one, when you are doing it with replacement, then probability of getting a red ball will be P equal to 10 by 25, 2 by 5. If you draw it next time, because you have replaced, this P will remain the same. It will not change. Okay? You understand what I said? We are getting red balls from there. 5 balls being selected one by one with replacement, without replacement, and probability of getting red ball 2 by 5, it is constant. This will remain a constant during the experiment. So this one is a Bernoulli's trial. But in the second case, when you have drawn a red ball, first time probability is 10 by 25. P1 I am taking. 2 by 5, true. Next time, one ball you have kept out. So how many red balls are there? 9. It will be 9 by 24. So this is 3 by 8. See, probability is not remaining the same. So the second experiment will not be a Bernoullian trial. Not a Bernoulli's trial. Okay, this one is a Bernoulli trial, or example of Bernoulli's trial. Clear? This is not example of Bernoulli's trial. Second case is not the example of Bernoulli's trial. Clear? So far you have got the idea of trial and Bernoulli's trial. Binomial distribution. Why this concept is required? Let me tell you one practical problem. Okay? Let there be 5 trials. First you assume the experiment is like this. Let a coin, you take a coin only. Coin is being tossed 5 times. Coin is being tossed 5 times. Okay? Let S and F represent the event denoting success and failure respectively. Okay? Now, getting a success is getting a head over there. Assume that getting a success means getting a head over there. Now in these 5 trials, if I tell you one success is there, let there be one success. One success means which trial success is coming, that you don't know. It may be like this, S, then failure, failure, failure. There will be F, S, F, F, and another F. There may be F, F, S, F. How many cases? 5 cases will be there. There may be F, F, S, F, F. There may be 4F, then S, isn't it? So how many cases? How many cases have I got there? I have got 5 cases over there. So getting one success when a coin tossed 5 times, first time success, then failure, then failure, then failure. First time failure, then success, because I am talking about one success. Let there be one success. We get these many cases. How many cases? 5 cases are there. In the language of permutation, if you say that I can tell you how many ways can be arranged, it will be 5 factorial that divide by how many? Those 5 you are arranging and those 4 are repeated. So it will be factorial 5 by factorial 4. So 5 cases are there. Now I am considering a case. Let there be 2 successes. Then what will happen? 2 successes means that we denote by S only. There is going to be S, F, F. So many cases will be there, isn't it? I have to arrange all these S and F. It will take long time for me to arrange. And even if I do it by the concept of this arrangement, permutation and combination, it is going to be factorial 5 by factorial 3 into factorial 2. This time it won't be a problem. Factorial 5 you all know, this is 120. 6 into 12, answer is going to be 10. But problem arises when I am saying that a coin is being tossed 30 times. Okay? How many ways you can get? 20 successes. You will spend the whole day to get the answer. Because all those arrangements you have to consider. You have to appoint one of your staff to help you out. Finally, end of the day, you will be getting bored and leave the experiment. If people have asked to do it for 200 times or 100 times, no one will do that manner. And here, we can use binomial distribution to get the probability of 20 successes out of 40 trials or 50 or 200, 40,000, whatever, quickly. So we need to know how binomial distribution was developed to explain, to find the probability when number of successes is large. Okay? My aim is not deriving everything here, but you need to know how the concept was developed. Random variable, probability distribution of random variable, you have the idea. Tabular representation of probability and values of random variable, you have related, you found mean, variance, everything. With large number of trials, how a probability distribution concept can be associated, that I am going to explain. Suppose you are performing an experiment of tossing a coin. You are tossing a coin 3 times. A coin is being tossed thrice, 3 times. Okay? What is the probability distribution by remembering that success and failure case? But I want to generalize. That's why I will not write the probabilities exclusively. And this is the case of Bernoulli's trial. So we will assume that success, that we denote by S, failure we denote by F. Success by S, failure by F. And coin is tossed 3 times. So what are the cases? That sample space contains what? This is S, F, F, you know. F, S, F, you know. There may be F, F, S. Then S, S, F. There may be F, S, S. Sorry, I'm looking for F, S, S. There may be S, F, S. And then 3 S's may be there. 3 failures also may be there. Okay. Now we have to write the probability of success. P success we are taking as P. P failure we are taking as Q. Instead of writing half all these things, I am taking as P and Q because I will generalize after this one. Okay, formula derivation is not important. I am not going to derive formula also. Little bit interest is left for deriving formula, but I need to explain how the concept of binomial distribution came into scenario. This P plus Q always should be equal to 1, isn't it? Now, if we associate the random variable X, X denoting number of successes. X is the random variable denoting denoting success. Success means getting head over there. Then x can take what values x can take, you know it very well. If I start writing values of x and then corresponding probabilities, then probability distribution you have the idea. It may be 0, 1, 2 or 3. Isn't it? Then I am writing Px equal to x. How can I write Px equal to x? 0 means no success. This is probability of f, and f. Events are independent. You write this as Pf into Pf into Pf. Understand what I am doing? Pf, what you have taken? It is Q. Q. This is nothing but Q. You understand? Because here events are independent. So we can do the calculation this manner. Then what happened in this case? It will be P. Which case is there? That is SFF, FSF and FFS. You write PSFF or PFSF. All events are independent. This is the condition for Bernoulli's trial, isn't it? So this is going to be probability in the first case. If you write this manner, it is PQQ plus. Events are mutually exclusive also. You can add this as sum of these three probabilities. So probability in the second case will be what? Failure, and then failure. In the second case, failure. So just repetition of the first case. PQ square coming thrice. We write 3PQ square. You understand? When there are two successes, how to write it? This is going to be probability of two successes means PSSF, FSS, SFS. And these events are mutually exclusive. It will be probability of this plus probability of this plus probability of this. And events are independent. So if you start writing here P into Q, because probability of success is P, this one P, this one Q, and this one Q, P. Again the repetition, you see, it will be P, Q, P. So this is going to be 3P square Q. And the last case, it is going to be PSSS. This is going to be probability of S is what? P into P. This is PQ. See, it is very interesting. This is the beauty of mathematics. You got the structure here. Now you have to frame the formula. Okay? So I'm just mixing up that binomial theorem here. I mean just expansion. Don't say binomial theorem. I'm just taking the expansion of P plus Q to the power n. No, not n here. You take P plus Q to the power 3. What is the expansion? All of you know. This will give you PQ, 3P square Q, 3PQ square plus QQ. See, all these terms have come one by one. This is the first, this is the second, third, fourth, all the terms present over there. First case, what do you get? PQ is this one, probability of 3 successes. This is probability of 3 successes. SSS. Here, this is 3 times probability of, you just write 2 success, 1 failure. Because they are all similar, no? Here, what is the probability you got? 3 times probability of 1 success and 2 failure. And this time, it is probability of 3 failures. Isn't it? Just 3 failures. 3F. Okay? And another thing, if by using combination symbol, I want to write all these expressions, then the first one remains the same, PQ. 3 is nothing but 3C1. You know very well. So I am writing 3C1 P square Q. This P square also is split. This P square you write P to the power 3 minus 1. Q to the power 1 plus 3 into this P you write 3 minus 2 Q to the power 2 plus QQ. Okay. So very interesting to note that when there is one success that I am writing, even the last term also you can write, first term also you can write, that 3C3 also. This PQ, no? You start writing from end, it will look better. Just a minute. It will look better if I start writing from the end. This I am writing, the first case I got QQ, no? This is nothing but just Q into Q into Q, QQ. This is nothing but 3C1 P to the power 1 Q to the power 3 minus 1. This is nothing but 3C2 P to the power 2 Q to the power 3 minus 2, and this is PQ. Got it? So that this case is going to be for 3 successes. We can write 3C3PQ. 3C3 has value 1. This one how will you write? Written already. This case. This is 3C2 P to the power 2 Q to the power 3 minus 2. This one is what? 3C1, because one success is there. This case P to the power 1 Q to the power 3 minus 1. And here 3 failures, it will be QQ. Okay. This is for when you have tossed the coin 3 times. You have performed the experiment 3 times. Then I can express all the results in terms of this binomial. Okay. All these terms are coming one by one. 3C2 P square stands for 2 successes. 3C1 P to the power for 1 success. Okay. So this thing if we rewrite, then it will be PQ. This you write first. 3PQ square 3P square Q plus QQ. This is nothing but PQ 3C1 P to the power 1 Q to the power 2 3C2 P to the power 2 Q to the power 1 and QQ. See, sum of the indices is equal to 3. Now let us go directly for writing the formula for P plus Q to the power n. Why I am taking this? Because who told you that experiment is restricted to 3 tiles only? It may be n number of tiles. So in that case, it is going to be P to the power n for n successes. Then NC1. Okay, if I write P to the power n first. Okay, let me write this thing as in the ascending power of P. Okay, so you write Q plus P to the power n. This is Q to the power n. No success. 1 success, NC1. Here it was 3C1, 3C2. There it will be NC1 P arise once, Q n minus 1 times. Plus NC2 P to the power 2 Q to the power n minus 2 plus, you write once more, NC3 P to the power 3. This way, if I take the arbitrary term, suppose I am writing, this was for 2 successes, 3 successes, I am writing for X number of successes. How will I write that? For X number of successes, it will be NCX P to the power X Q to the power n minus X. Plus this way it continues. Last one is P to the power n for n successes. Purpose is solved. We got probability of 3 successes, 1, 2, and the most important thing is that we have generalized the result. probability of x successes is going to be equal to what? So in these trials of a random experiment, probability of x number of successes going to be equal to, we denote this one by fx. This is nothing but ncx p to the power x q to the power n minus x. Okay. If you start writing this, the probability distribution here, this fx, don't worry, this fx we have taken the probability distribution function. Already taken in the first chapter, the same thing I have taken. That x can take value 0, 1, 2, 3 like that. So if I write the probability distribution here, then for x equal to x, fx stands for what? Actually it is fx equal to x or px equal to x. We are habituated writing this. We can write this symbol also. Okay. When x equal to 0, it is going to be nc0 p to the power 0 q to the power n. For 1, it is nc1 p to the power 1 q to the power n minus 1. This way, if you start writing for x equal to x, in that case, it is ncx p to the power x q to the power n minus x. And finally, if we write for the last one, then for n number of successes, it is going to be p to the power n. Hope all of you have understood how binomial distribution came into the scenario in a random experiment in Bernoulli's trial that I have tried to explain. The conceptual part is done. Now just application. I remind you before you go for application that n stands for number of trials, x is the number of successes, p is the probability of success, q is the probability of failure. When x successes is there, index of p is going to be x and failure n minus x. Sum of these two will be equal to n always. Clear? So let us start with the easiest one here. The easiest problem. Why? Die is thrown 5 times, probability of obtaining exactly 3 twos. 2 is the success over there. I was telling 6 is the success, but here the author has changed. They are saying that it is 2. Success is 2. What is the probability of obtaining exactly 3 twos? That I am going to explain. So a die has 6 faces, you know. What is the value of p here? Probability of getting 2. Just one case. It will be 1 by 6. Q is what? 1 minus 1 by 6 or simply 5 by 6. So how do you answer this? Probability of obtaining. So always when you are going to solve the problem, you write fx. It is ncx p to the power x q to the power n minus x. What is n over there? N also you need to write. It is 5. What you are going to find? Exactly 3 twos. So x equal to 3 here. X is equal to 3. It will be 5c3 1 by 6 to the power 3 5 by 6 to the power 5 minus 3. So 5c3 you all know, factorial 5, factorial 3 into factorial 2, all these things you know, it will come 10. 10 into 25 by 6 to the power 5. In exam you must do it. Right now I am not doing it. You understood? Then it's fine. If you have understood, then let us do for next one. Die is thrown 4 times. Find the probability of getting exactly 3 successes Okay. Exactly 4 successes, at most 2 successes. Let me answer. Not a difficult one. You also can do it with me. Hope you are ready with your pen and paper. Die thrown 4 times. You write just n equal to 4 and getting 1 or 6. Bit different from previous one. Getting 1 or 6. Probability of getting 1 or 6. I mean out of 6 cases. 1, 2, 3, 4, 5, 6. 2 are possible cases. 2 by 6. This is 1/3. Getting exactly 3 successes we are going to consider. So x going to be equal to 3. First case. So first case answer will be what? Before that you need to write fx. Never forget to write fx. Fx is ncx p to the power x q to the power n minus x. Okay. So n you put 4 c3 1/3 to the power 3. And what is q? This is p, no? Q will be what? 1 minus p. It is constant for Bernoulli's trial that I told you so many times. I tell you again. With MCQ question can arise from any corner. Okay? It is 2 by 3 to the power 4 minus 3, 1. This will be 4 into 2 by 3 to the power 4. You can find it. 8 by 81. Clear? Second part. This is the first part. We got. Second part, how will you write? Exactly 4 successes, similar manner. Here you found F3. We are going to find F4 here. 4C4. 1 by 3 to the power 4. 2 by 3 to the power 0. So this is just 1 by 81. And in the third case, at most 2 successes. Like the probability distribution chapter, that introductory chapter, the way we have written, you write the same manner. At most 2 successes will be what? This is going to be F0, no success. F1, 1 success. F2, 2 successes. F0 will be what? Formula is there with you. F0, you put over there. F0 is what? N is 4. So 4C0 P to the power 0 Q to the power 4 minus 0 plus F1 NC1 P to the power 1 Q to the power 3 plus NC2 P to the power 2 Q to the power 2. Clear? Understood? Don't write NC2. N value is 4. You put directly the value 4 over there. No need to carry n over there. You just write the values now. It is q to the power 4. Q to the power 4 means 2 by 3 to the power 4. 4 into 1/3. 2 by 3 cube. 4c2 is 6. You know very well. It is 1 by 3 to the power 2. 2 by 3 to the power 2. Got it? Just little bit simplification is required. 16 by 81 plus 8. 8 4s are 32 by 81 plus 6 into 4 divided by 81. You just add these. 40, 72 by 81. So easy. Understand? At most 2 successes, probability is this. Clear? Next one, I'm just discussing a few types. In 4 throws with a pair of dice, n going to be 4 and pair of dice. What is the probability of throwing doublet? 3, 4, 5, 6. 1, 2, 3, 4, 5, 6. We have to get probability of doublet. That is 1, 1. 2, 2, you know, 3, 3, 4, 4, 5, 5, 6 cases are there, and probability of getting a doublet, how many cases are there? Already discussed in many sums. It is 6 into 6, 36 cases. So P is going to be 6 by 36, and Q is what? 1 minus 1 by 6, that is 5 by 6. So you write fx here first. This is your duty. 4cx p to the power x and q to the power n q to the power 4 minus x. You put pq also. 4cx 1 by 6 to the power x, 5 by 6 to the power 4 minus x. Then what probability you are going to find? At least twice. In 4 throws, n is 4, at least twice. You need to find F2, required probability F2 plus F3 plus F4. Can simplify also, you write 1 minus F0 minus F1. At least one term is reduced. What is F0 here? 4C0, 5 by 6 to the power 4. F1 is what? 4C1, 1 by 6 to the power 1, 5 by 6 to the power 3. So this is 1 minus 5 to the power 4. My God. That is 625 by 1296. 4 into 125 by 1296. So this is going to be 1 minus 625 by 1296, 500 by 1296. Take 1296 LCM. This minus 5 to then 11. This is going to be 161 by 1296. Hope you have understood. 5 cards are drawn successively with replacement from a well shuffled deck of 52 cards. What is the probability that all 5 cards are spades, only 3 are spades, none is spade? This is another type of sum where card selection is there, and the problem is with drawing spade. Okay, so you know, out of full pack of 52 cards, 13 are spades. So P for this problem going to be 13 by 52. This is 1/4. Okay, n equal to 5 and Q, you know, 1 minus P. I have written all the information, then I will write it for Fx, which is nothing but probability of x equal to x, and it is given by 5cx p to the power x, q to the power n minus x. I will suggest to write this before any exam, school or board exam. You write this thing and then you proceed. So for the first part of the problem, all 5 are spades. So what will be the probability here? All 5 spades means x will be equal to 5 over there. So required probability is F5. This is nothing but 5C5 P to the power 5 Q to the power 0. So it is simply P to the power 5, that is 1 by 4 to the power 5. Okay. So this is 1 by 4 to the power 5 is 2 to the power 10, that is 1024. Second part, only 3 cards are spades. So put x equal to 3. Only 3 they said. Okay. So here we will be putting x equal to 3. So F3 is requirement. It is 5C3. P to the power 3. P is what? 1 by 4. And then 3 by 4. You always check that sum of these two will be equal to n given over there. 3 plus 2 is 5. So perfectly alright. It is 10, 9, 1024. Divide by 2. Numerator and denominator, it will be 45 by 512. Okay. And for part 3, none is paid. None is paid means x will be equal to 0. So you are going to find the value of f0 over there. f0 will be what? 5c0 p to the power 0 q to the power 5 minus 0. So simply q to the power 5, 3 by 4 to the power 5, denominator 1024, 3 to the power 5, 3 to the power 4, 81 into 3, 243. Clear? Hope you have understood. Let us go for next one. The probability of a man hitting a target. Hope all of you are ready with your pen and paper to solve it with me. Okay? You don't have to waste extra time anywhere. If you are doing it with me, means it's done. So my request, these videos, I mean these sessions, live session, whatever you say, is made for you so that you can practice with me. Even you can complete the sum before I do it here. Okay? This will be your aim. Then my effort will be fruitful. Your effort also. Probability of a man hitting a target is 1 by 2. Practicing something like gun or toy gun, obviously. Gone to a mela and you are trying shooting practice over there. How many times he fired so that probability of hitting the target at least once is more than 90%. This is a different type. Kind of sum I have explained so far similar, but here it is different. Okay? How many times should you fire? One is given that probability is half. So you write the information P equal to half. This implies Q is also half. Binomial Bernoullian trial. So P and Q will not change. This is one of the important characteristics. I will remind you one by one. All those. Okay? We have listed before. I just remind you. P and Q will not change during the experiment. During his firing. How many times must he fire so that probability of hitting the target at least once? So it is better you write n is not known. N is n over there. X will decide later. So let us write the value of fx first. This will be a strategy to write the value of fx. So fx is what? Ncx p to the power x q to the power n minus x. N we don't know, x also we don't know, but pq we know. It is half to the power x, half to the power n minus x. If you add all these, it will be ncx half to the power, addition takes place in indices, it will be half to the power n. Clear? Now it is given that this ncx half to the power x at least once means, let us write the probability of at least once. Probability of at least once will be equal to sum of these cases f1, f2 continues this manner up to fn. Okay. So how do you get at least once? At least once you will get when you consider total probability is 1 always, that minus f0. X equal to 0 you subtract from there. Okay. So this thing for x equal to 0, that probability, let us write it for f0 first. f0 is what? NC0 half to the power 0, and it is actually half to the power not 0. I have written simplified version is half to the power n. So this is half to the power n. NC0 you know 1. So this thing is half to the power n. Now given that, what is given over there? That half to the power n, this thing is at least 1, this is 1 minus f0. This exceeds 90%. Alright, 90% means it will be 1 minus half to the power n. This is f0, no? But we have to write 1 minus f0. 1 minus f0 is what? 1 minus half to the power n. So write 1 minus this thing given. 1 minus half to the power n is given than 90 by 100. So 1 minus 90 by 100 is greater than half to the power n. 10 by 100. 10 by 100, not 10 by 10. 10 by 100 is greater than 1 by 2 to the power n. So 2 to the power n is greater than 10. What is going to be the value of n? This implies n equal to, for what value? No need to use log. N should be an integer. A common concept. No log, no calculator. If you take n equal to 3, it is 8. 8 is not exceeding 10. So you should take the next integer, that is n equal to 4. Am I clear? So value of n going to be equal to 4. Clear? Understand? Now this time problem is bit different. Determination of frequency of success. It's a common problem in any distribution. All this probability why you are doing. Suppose there are this problem only. Let us set 100 sets of 5 tosses of an unbiased coin. This is a practical application of probability. In how many cases do you expect to get 3 heads and 2 tails? We haven't done this kind of sums so far. How to do it? Let me start. 100 sets of 5 tosses of an unbiased coin. 5 tosses. So n is equal to 5. Unbiased coin means P and Q both are equal to half. It's known. 3 heads and 2 tails, that probability also you can find. What is that probability? After finding the probability, you multiply the result by 100. If 1000 sets were there, multiply the result by 1000. Then only you will get in how many cases there are 3 heads and 2 tails. Should remember the method. Another type, very important type for your board examinations, obviously for forthcoming school examinations also. So P half and Q half. 3 heads and 2 tails. What will be the probability? Let us find it first. So you will be writing fx. Don't forget to write it is ncx p to the power x q to the power n minus x. N is what? 5. 5cx half to the power x half to the power. If you add these two indices, it is going to be 5 to the power x multiplied by half to the power n. Isn't it? Now here 3 heads and 2 tails. So you need f3. F3 is what? 5c3 half to the power 5. N equal to 5. So 10 by 32. Then how to get the required number? In this problem, n, capital N, number of sets given 100. If it is given 1000, we take capital N equal to 1000. So required number in the first case going to be n into this probability. Probability of x equal to 3. The same concept we will apply in future. That is in Poisson distribution also. Same concept. So n is 100 over there. This multiplied by 10 by 32. This you calculate 2, 5, 16, 4, 125 by 4. This is 31 point. 31 point what? 31 point, say something like, if you divide 31 then 1 then 0.1025, something like this. Required number, how it can be 31.25? You cannot take more than that. So 0.25 you have to exclude. So answer to the first part going to be 3 heads and 2 tails. How many cases you will get? In 100 sets of observation, for the first part answer is 31. Second part answer is similar to this. How to get it? At least 3 heads. So here probability is going to be F3, F4, F5. F3 you already got. What is F3 over there? 5 C3 half to the power 5. Follow this thing. F4, put x equal to 4 over there. And n equal to 5 always. 5 C4 half to the power 5. F5 will be 5 C5 half to the power 5. So 10 by 32. 5 by 32, 1 by 32. Got it? So this is 16 by 32, that is half. So how to get required number here? At least 3 heads. So required number is going to be equal to big N, number of cases, that multiplied by this probability. Actually, this is going to be mean in our discussion, following discussion. It will be 100 multiplied by half. This is equal to 50. Okay. We are back to this concept again. What we did in the previous chapter, mean of probability distribution. Same thing is true for mean of binomial distribution. Expected value of binomial distribution is the average number of successes in intervals. Okay. So if I remind you that binomial distribution table which we did before, here in the first row you write fx. No, first row you just write x equal to x. Second row you write fx. Here it is x equal to x. Here it is px equal to x, that we have taken as fx. Okay. Now you write 0 here. This probability is what? This probability, it may be 1, it may be 2, it may be 3, it may be all intervals. Okay. N. So here probability is what? That you know very well. NC0 q to the power n. This is just q to the power n. P is the probability of success. Q is probability of failure. It is NC1 P q to the power n minus 1. NC2 P square q to the power n minus 2. NC3 P cube. This way it is till p to the power n. Okay. I am not going to derive anything. Just if I tell you how to find the mean, the way we have defined in case of probability distribution in the previous chapter, here mean number of successes is going to be mean mu or x bar, whatever you say. So long statistical inference is not started, you take mu or x bar, it doesn't matter. There we will take it. So this is going to be what? 0 into q to the power n pixi. Remember it? We did it. NC1 p to the power n minus 1 into q. Like this only we have to continue. This is Next one is 2 into nc2 p to the power n minus 2 q square. This way if you continue, it will be ncn into p to the power n. What is the sum of this thing? We are avoiding calculus. Sorry, calculus may not be required. Binomial theorem is enough. We are avoiding that calculation also, because in applied mathematics, huge derivation is not required. Just apply. Where do you apply? In practical field, in daily life. Okay. Mean is required. Somebody asked you to find the mean number of successes. You need to use. You are something like prompt engineer nowadays, isn't it? So applied mathematics students will find the application very first than pure mathematics students. Everything is applicable in mathematics. This you have to believe. So this sum, if you want to do, this will be n into p. Okay. Derivation not required. Again, I am telling you, even for your board examination, I am sharing my past 3 decades of experience teaching mathematics. Okay. So derivation, this kind of derivation will never be there. You just remember mean, x bar or mu, whatever you say, that is NP. In all the previous calculations, you could have done this thing like the previous one. I'll show you example. Before that, let us know variance of binomial distribution. What is that? Variance of binomial distribution, the spread of dispersion of number of successes from the mean. If you calculate variance by remembering the formula what we did in the first chapter, then Varx is going to be equal to NPQ. This will represent what? Meaning is same, but you need to remember variance of binomial distribution measures the spread or dispersion of number of successes from the mean. Okay, already explained. I am not wasting time here. Standard deviation, it is square root of standard deviation x is going to be under root of Varx, which is given by NPQ under root. It is denoted by the letter sigma. Don't be confused. Now one application, let us see. Tossing a coin. Tossing a fair coin 10 times. What are the mean, variance and standard deviation of getting heads? Very easy to answer. Everyone can do it because formula you got n equal to 10. So mean will be what? X bar equal to mu equal to NP. This is nothing but P, you know. Tossing a coin, unbiased coin, P and Q both are equal to half. Isn't it? So NP means 10 into half. This is 5. Okay. This is mean. Average number of cases you will find head is 5. Getting heads. That will form. And then variance. Variance will be what? NPQ. 10, half, and then another half. So this will be 5 by 2, 2.5. And then standard deviation, SD. This will be under root 10 by 4. This is root 10 by 2. Just simplify. Okay. Question I am just discussing. I am not going to solve all these. Rolling a fair 6-sided die 20 times. What are the mean, variance, standard deviation of rolling a 4? Here just the probability will be changed. Formula will not change. P is what? Rolling a 4. 6 spaces are there. Getting 4 will be 1 by 6. Not getting will be 5 by 6. N equal to 20. You can find everything. No need to waste time with it. Then quality control. Again, similar problem. Factory produces light bulbs and probability that a bulb is defective is 0.02 100 bulbs are test. What are the mean, variance? So here probability given, N also given. You just use the formula over there. Clear? Now go for this one. Mean of binomial distribution is 20 and standard deviation 4. Find the parameter. Okay. Mean of binomial distribution 20. So mu, that x bar or NP 20 in the problem. And SD under root NPQ is equal to 4. SD given, see, not variance. So this implies what? You put the value of NP there. 20 into Q equal to 4. Make square. Squaring, what do you get? 20Q equal to 16. 16 by 20, this is 4 by 5. Parameter means what? Binomial distribution parameters are N, P and Q. If you know N and P, then everything is done. So Q you may not include because P plus Q going to be equal to 1. So parameters means NP. Binomial distribution can be stated this manner only, just N and P given. Then everything is known. N you haven't found. Q is 4 by 5 since NP equal to 20. You put it over there. Q 4 by 5. So P is what? 1 minus 4 by 5, that is 1 by 5. N into 1 by 5 equal to 20. So N is equal to 100. Clear? You have understood? This kind of problem may arise as 2 mark. 1 mark also possible. Next one. The mean and variance of binomial distribution given. Find Px greater than 1. Mean is what? For this, NP is equal to 4 by 3. NPQ is 8 by 9. You have to find Px greater than 1. That you can find by remembering the fact P plus Q equal to 1 and then finding the value of N. Then only you can write Px greater than 1 will be what? Tell. Px greater than 1 means it will be P x equal to 2 plus Px equal to 3 plus this way P x is equal to N. Clear? So we need to get N. Dividing 2 by 1. If we divide 2 by 1, what do you get? Q will be 8 by 9 by 4 by 3. So 8 into 3 by 4 into 9. 2. So what is the value of P? P is equal to 1/3. If P equal to 1/3, then you are getting N from there. From 1, N equal to 4 by 3 by 1 by 3. This is 4 only. If N equal to 4, then you can find Px greater than 1. You simplify it. This you write 1 minus P x less than equal to 1. That is 1 minus P x equal to 0. We often use this technique. We are using it. So finding Px equal to 0 means it is actually F0 and F1. Where is your F? Forgot to write. Never do it. In the beginning of problem, in the beginning of any calculation in probability distribution, this is compulsory to write the value of Fx for you. It is 4Cx. P to the power x, Q to the power n minus x. N is found, P also found. So it is 1 minus 4C0 P to the power x. This multiplied by 2/3 to the power 4 minus 4C1 1 2 by 3 cube. Okay. So on simplification, this is going to be 1 minus 16 by 81 4 into 8 by 81, isn't it? So take the LCM. 81 minus 16 minus 32. 48. So it is 33 by 81. Keep it this manner. 81 minus how much? 48. You just subtract. It is 33 by 81. 3 is getting cancelled, of course. Clear? I hope all of you have understood binomial distribution. The problem sheet is already shared with you. You will find in the description box also. You must practice sums from there. Okay?